fluid mechanics. As you know that we are discussing chapter number 7 of your textbook, which is dimensional analysis, modeling, and similitude. So in the previous week, we discussed that how we perform the dimensional analysis, in which we determine the non-dimensional uh, products for the before the conduct of experiment. And now, once those non-dimensional products, which are also called pi terms, they are determined by either using method of repeating variable or by method of inspection. Then we need to in generally in most of the cases we need to prepare a model for a prototype. So prototype, let me recap which we discussed in the 2 weeks lecture, that the actual system for which we need to do the experiments, that is called prototype. And in most of the cases we need to make a scale up model or scale down model, depending upon whether we are investigating a very large system or very small system. So we have to prepare a model for that. So the physical system for which, so that model is the representation of a physical system, right? So model is the scale down or scale up model, and the actual system is the prototype, as it is shown in the this figure. And the above figure is the prototype, which is the actual system on which we need to calculate drag or anything we want, and there is a scale down model. So why we create a scale down model? Because they are easy to handle, but we need to be very careful that whatever we do on the model, and if there is any error, we would come to know about that error only when we conduct the experiment, or we see its results on the actual system. So now, before going forward, first of all, that when we scale it down, then we need one thing, we need to make sure that whatever we do on the model, they should replicate the actual flow conditions which are experienced by the prototype, which is the actual system. So for doing that, we write the pi terms in the for the prototype, which is determined by the dimensional analysis, and then we again write it the functional form in terms of pi terms for the model, right? And then in order so that this dependent pi term, pi1 and pi1m, they are equal, we need to make sure that the corresponding pi terms in the independent, like pi2 should be equal to pi2m, pi3 should be equal to pi3m, and so on. So only then, at the end of the experiment, uh, we can transfer the results which are obtained for the model, that can be transferred to the actual system. So the example we discussed, that the problem we discussed for the non-dimensionalization, non-dimensionalization, and for finding the pi terms for uh, for the drag force on a thin rectangular plate. We know that if we do the dimensional analysis, we can get some sort of this functional form in terms of non-dimensional form, right? And now this is for the actual system, which is prototype. So we can write it for the model as well. And then, because if we are scaling it down, so it means that if we decrease the width of the model, then we also need to alter the height of the model, right? So how to calculate those heights or widths? That is by geometric similarity. So it means that this first pi term of the model should be equal to the first pi term of the of the system. So from there we can get the width of the model, and similarly the velocity of which is to be used in the wind tunnel or water tunnel, that would be Vm. So that can be calculated by this equality of the second independent pi term. So if we do that, we can, and we call it dynamic similarity. And then drag force on the, because we are conducting the experiments on the model in the wind tunnel, which is, it means that we are going to calculate this drag force on the model. But for the actual system, we need to find the drag force. So that would be this D, and then we can calculate drag force for the actual system by the equality of the dependent pi term, right? So that is, and then in the last bit we discussed about the modal scale. So it is the ratio of model variable to the prototype variable. So it means that if we are talking about length scale, so and it is represented by lambda. So 1:10 means that we have scaled down the model 10 times. So if the actual length scale for the system was 100 or maybe 50 feet, so for the model it is only 5 feet. So then we would write lambda L is equal to 1:10 or 1/10. And similarly for the velocity scale, density scale, and viscosity scale, whatever variables are there, we can define these model scales. Now we can do a couple of numericals if there is no query from the last lecture. So let me know if you are clear about what we discussed in the last class, so that we can move forward. Okay, so now we do first problem related with modeling and similitude, that a long structural component of a bridge has an elliptical cross section. So here we can see that this cross section is elliptic, and it has got two dimensions, like in the flow direction it is h, and in the vertical direction it is d, right? So you can, if maybe I can make it a little bit more visible. Maybe now it would be a little bit better. So D is the vertical dimension, and H is the dimension in the flow direction, and V is the velocity, free stream velocity, which is coming on that structure. So it is known that when a steady wind blows past this type of bluff body, vortices may develop on the downside that are shed in a rectangular fashion, in a regular fashion. So you can see these vortices coming in the wake region, and this generation of these regular pattern of vortices, they are called von Karman shedding. So von Karman was the scientist which first observed this phenomena. So they called it von Karman shedding streak. So since these vortices can create a harmful periodic forces acting on the structure, it is important to determine the shedding frequency of this, that how it would oscillate due to the generation of these vortices, right? So let me go back to the normal view. So for this specific structure of interest, the actual bridge has a diameter of 0.1 meter and height of 0.3 meter. Height means that it is basically the length in the flow direction, h, not height, because here diameter is giving you the the flow normal direction, and h is the in the flow parallel direction. So h should be length of this here, and a wind velocity of 50 kilometer per hour. The shedding frequency is to be determined through the use of a small scale model that is to be tested in a water tunnel. Now, because we have got, because the people who did this experiment, they have got only water tunnel, so they are going to conduct it in a water tunnel. So it means that the density and viscosity values, they would be very much different for the model and the actual system, because actual system is operating in air, and the model on which we are going to conduct the experiments, that is to be in water tunnel. So now we need to determine the model dimension hm and the velocity at which the test should be performed. If the shedding frequency for the model now, if the shedding frequency for the model in the water tunnel is found to be 49.9 hertz, what is the corresponding frequency for the prototype? So it means that what would be the actual frequency of oscillation for this bridge, or the structural component of this bridge. So we know the usual drill. First of all, we write the functional form. So functional form, we know that here the, yes, anything, any query? Okay, maybe not. So just going back to the lecture, so we need to determine the shedding frequency. So for the actual bridge. So as I was saying, that we need to first of all need to determine the pi terms. So we know that in this, the dependent variable is the frequency of oscillation, which is written by omega here, right? Not W but omega, and then it is function of vertical height and the horizontal length, then decreasing velocity, density, and viscosity. So if we apply the method of repeating variable or anything like, or maybe method of inspection, because we know that there are total 6 variables, so we would have 3 pi terms by the use of Buckingham pi theorem. So we would eventually get to this omega d upon v function of d upon h and Reynolds number. Now, this pi term on the left hand side, if I take you back to the table which we discussed in the last class, here if you see that a problem where there is some kind of frequency of oscillation involved, there is omega L upon V. But what is this L here? That is the characteristic length. So for this bridge structure, the characteristic length they have taken, that is the vertical height. So that's why if you see that pi term, that is basically the Strouhal number. We call it Strouhal number. Omega, this characteristic length is a vertical height. So omega d upon v, which is the Strouhal number, and this is Reynolds number, rho v d upon mu. And if you notice that the characteristic length here, that is also used as the vertical height of this elliptic structure. Right, so now we need to determine these 3 things. So first of all, let me write it on the, let me see that I can write it there on the whiteboard, and then we can take it from there. So now let me write it again, because this is only written for the actual systems. So for the model, we can write this again: omega m dm vm function of dm hm rho m vm dm on mu n, right? So Now, if you read the statement here, first of all, we need to determine the model dimension HM. So, to determine HM, what we need to do that we need to equate this one and this one, this D upon H. So, if we equate that, so we can write dm upon hm is equal to d upon h, because we need to find h here, hm. So what we do that we just rearrange this. Hm would be equal to dm into h upon d. Now, diameter of the model, if you look here, diameter of the model is 20 mm, and then we have got the actual diameter 0.1 meter and h is equal to 0.3 meter. So we just put these values here. So it would be equal to 20 into 10 to the power minus 3 into h value, which is equal to zero point 0.3, and d value, which is equal to 0.1, right? So if we calculate the value of hm, that comes out to be 60 into 10 to the power minus 3 meters. So now one thing we can easily see that once we have scaled it down, then we didn't only change the that d variable, we also change the h variable accordingly, so that these two ratios for the actual system and the model, they are equal, right? So that is the beauty of non-dimensionalization, so that we talk about in dimensionless ratios. So after that, once we get that, after that we need to determine if we did through this and the velocity at which the test should be performed. Now we need to calculate the model velocity, which is Vm. So Vm can be calculated either by this left hand side pi terms, but in that case we also know that dm or actual d is not known to us. So this actual omega is not known to us. So that's why we just use this second term on the right hand side, which is the Reynolds number. So if I write the dynamic similarity for this, that would be equal to rho m vm dm upon mu m, that would be equal to rho vd upon mu, right? So from here vm would be equal to mu m upon mu, and then it would be rho upon rho m, and then we would have d upon dm and v. V is the actual velocity. So now we know all these values. That what is if I tell you here that this, because we are conducting the test in water tunnel, so this mu, which is the viscosity of water, that would be mu m, and that rho m would be 998, right? And actual system is operating in air, so that would be mu, and rho would be for the prototype. And then velocity, that is given in 50 kilometer per hour, so we need to multiply this velocity with 1000 and divided it with 3600 to get it into meter per second. So if we do that, so velocity would come out, velocity for the actual flow would be 50 into 1000 divided by 3600. So if we calculate that value, that would be 30.9 meter per second. So now if we put all these values, because we know d, dm, rho m, and um, mu, so we can calculate the value of vm. So Vm comes out to be, if we put the values, all of those values, so that comes out to be 4.79 meter per second. Now, this is a little bit more interesting, because if you remember that in the last class, that when we kind of saw that if we reduce the size of the system to the model, then we need to have more velocity. Like if I correctly remember, if I take you back there on the whiteboard, we did the calculation. So in this case, the actual velocity was 2 feet per second, because we scaled it down by 100 times. So for the model, we needed to provide 100 times more velocity, right? But here it is actually the velocity for the model has been reduced. So that is very, it means that there is something else which is in play here. So if you remember that for this example, we took that that the model where the model is operating, the fluid where the model is operating and where the actual system is operating, that was the same thing. But in this problem, because the actual system is operating in air and the model is being tested in water tunnel, so these two terms, which are ratio mu m upon mu and rho m upon rho, these two terms are not one. So that's why we are experiencing a reduction in velocity rather than increase in velocity, because these ratios are such that the model velocity should reduce. So uh, always try to analyze the what does it mean, the numerical value. So it is important to get numerical value, but you need to interpret it physically, that what does it mean and whether it actually makes sense or not. So you should think a little bit more about the numerical value, just to make sure that whatever calculation you have done, that is correct. So that was VM calculation, and then if we see that what is the last part for this, that is if the shedding frequency for the model is found to be 49.9, what is the corresponding frequency of the prototype? So now in this case, we need to equate the pi terms on the left hand side. So let me show you that. So if we see here that we have got WD upon V, so omega D upon V and omega M dm upon V. So we need to equate them. So omega D upon V and omega M dm upon Vm. Right. So from here, omega would be equal to I can write dm upon d and v upon vm into dm into omega m. Omega m, if you see that is given to be 49.9 hertz. So we need to calculate its value. So if we put in the values, So that would be equal to dm. We know that 20 into 10 to the power minus 3 meter, and then the value of d is 0.1 meter, and then uh, actual velocity is 13.9 meter per second, and the velocity of the model which we calculated, that is 4.79 meter per second, and then mega m is 49.9 hertz. So if we calculate the oscillating frequency for that bridge component, so that comes out to be 29.0 hertz. So that is the thing, that how we transfer the results which we obtained for the dependent pi term in the model, how to transfer back to the actual system. So that was first numerical. If there is any query, you can ask. Otherwise, we can move on to the couple of more numericals. Okay, so it seems that everything is good.
सर इसमें से कंपेयर करनी पड़ती हैं वैल्यूज, जैसे कि डी करो डीएम ले लिया बोथ साइड्स में.
Okay, is it a question?
यस सर.
जी पूछिए मैथ प्लीज.
सर दोनों तरफ सर इक्वल तरह जैसे सर वो सिंबल यूज करने हैं यूनिट्स.
हाँ, ये जो पाई टर्म्स हैं, हाँ, अगर मैं आपको वो फंक्शनल फॉर्म पे ले जाऊं, मैथ खालिद, ये देखें ना, ये जो ऊपर हमने फंक्शनल फॉर्म लिखी है, ये इट इज फॉर द एक्चुअल सिस्टम. ओमेगा डी अपॉन वी इज फंक्शन ऑफ डी अपॉन एच इनटू रो वी डी अपॉन म्यू, right? And then here we have written the same thing for the model. Matt Khalid,
Yes,
do
sir.
you and then we need to first of all, because we need to take this functional form to the wind tunnel or water tunnel where we need to conduct the experiment. So it means that for that we need to determine either the dimension or the velocity which we need to use in water tunnel and wind tunnel. Once we do that, we are good to go to perform the experiments. And then we perform the experiments, and when we perform the experiments on the model, we determine this term. We get this term, right? This which is circled by green, and then because we get this for the model which is scaled down model, but we need the results for the actual system. Actual system is this one, this way. So we need to equate them to get the variable which is of interest, which is omega in this case, which is oscillating frequency. Is it clear, or you have
Yes,
got any other question?
No, sir, clear, sir.
Okay, thank you, Mayor Khalid, for asking this. Maybe it would help others as well. So I usually encourage a little bit more interactive session, but because I can't do that here, because if I ask, there is very little response. So please try to ask as many questions at the spot as you can. So it would help you and help me to make your understanding better. Okay, so this was first numerical. So now we do a couple of short numericals. So a model of a submarine. Now we are talking about a submarine which is scale 1 to 15. Is to be tested at 180 feet per second, and in a wind tunnel. Now this model scale, this is the length scale which is given. So that is given to us, that is it is 1 to 15. So if I write it here, what does it mean? So it means that it means that we are talking about lambda length. So lambda length, which is basically equal to Lm upon L, that is 1 divided by 50, right? So now in a wind tunnel with standard sea level, okay, a model of submarine, I have told you that what is the scale, is to be tested at 180 feet per second. So this 180 feet per second is the is the value of velocity in the wind tunnel. I think wind it is. Let me check. In a wind tunnel, okay, with standard sea level air. While the prototype will be operated in seawater, we all know that submarine operates in seawater. Determine the speed of the prototype to ensure Reynolds number similarity. The dynamic viscosity of air and sea water is 1.57 and 1.26, 10 to the power minus 4 and 10 to the power minus 5 feet per second. So it is quite simple that we need to, because we are talking about, first of all, we write the velocity of the model, which is 180 feet per second. And because it is a kind of dynamic similarity we are talking about. So for the dynamic similarity, we know that Reynolds number for the actual prototype should be equal to the Reynolds number of the model. So we know that Reynolds number can be written by V into length, characteristic length, and then rho mu into rho m v m and mu m. And we know that dynamic viscosity that is equal to mu m upon mu upon rho. So we replace that here, and then we can write VL upon mu and Vm Lm. And now we need to calculate the velocity of the prototype. It means that we need to calculate this velocity, which is v. So v would be equal to Lm upon L, and this is new we call it new. How do we write it? New, nu, and this is mu and nu. So we know that from our F11 knowledge. So and then it is Vn, right? So now we know that Lm upon L is 1.15, 1.15, and then nu upon nu m, if we talk about, so nu is 1.28 into 10 to the power minus 5, and then nu m, that is equal to 1.57 into 10 to the power minus 4, and Vm, which is given to us, that is 180. And then from here we can calculate the value of velocity with which submarine out to move, that is 0.963 feet per second. So now you can easily see that for the actual submarine, the velocity is quite less, but because we scale it down by 15, and then we are also changing the fluid in which we are conducting the test. So the velocity, actual velocity for the model where we needed to conduct the test, that was 180, but the velocity with which the submarine would move for the given flow condition, that would be 0.963 feet per second, which is quite minute, right? So I hope that you understand that we need to change the velocity considerably when we change the dimensions of the model with respect to actual system. So this was one numerical, and then the second numerical, that is also kind of similarity related with similarity, the fluid dynamic characteristics of now in this it was about the submarine, and now it is about an aeroplane flying 250 mile per hour, and the velocity is 240 mile per hour at 10,000 feet. We know that at 10,000 altitude, the viscosity and density becomes low, quite low as compared to sea level, are to be investigated with the aid of 1:20. So it means that lambda L, which is ratio of length of model divided by ratio of length of actual system, which is aeroplane in this case, that is 1 to 20. If the model tests are to be performed in a wind tunnel using standard air, now that is at the sea level. So what is the required air velocity in the wind tunnel? So that is the same. We are talking about dynamic similarity, and now we need to again use this equation, sorry, which I have written here. This equation. Let's see. So in this equation, if you see that we need to determine the uh, velocity Vm. So we need to calculate Vm. So all other properties are given. V, I think 240 mile per hour, and uh, Lm upon L, that is 1 by 20, and then rho values for the model and actual 10,000 feet they are given in the data, and we just need to calculate the velocity. So if we calculate the, and then uh, if we do the calculation by putting in the values, because we need to calculate Vm. So I would leave those calculations to your calculator, and instead if I write the value of that Vm, that comes out to be 3750 mile per hour, right? So now if you see the statement here, the last bit is this a realistic velocity? So we know that it is very difficult to get 3750 mile per hour in a wind tunnel. So it is not realistic. So what is the alternative now? So it means that either we conduct the experiments in water tunnel, maybe that would ease the this very high value of velocity. Maybe it would be a little bit less, which can be achieved in the water tunnel. Or second thing we can do, that the model we have created, maybe we need to scale it a little bit less aggressively. It means that maybe 1:5 would be more pertinent, or 1:10. So the purpose of this numerical was just to tell you that whatever we cannot blindly do the scaling down. We need to make sure that the velocity which we are getting after the scaling down, that should be a realistic value which can be achieved by the apparatus which is in the lab, right? So either we do it by changing the fluid as from air to water, or we can use less aggressive scaling down. Like in this case, it was 1:20, so maybe 1:5. If we do that, in that case, the velocity would be divided here by 4. Maybe it would be manageable or not. It depends on the apparatus we have got in the lab. So we need to be very careful before we do the scaling down for the model, that whether the flow conditions which are required to replicate the system level flow field, that is feasible or not, which was clearly not feasible in this case. So that was the purpose of showing this small tool miracles. So these are some of the problems, and please read through the practical aspects of using models. So I try to tell you a little, one or two practical aspects by the help of these miracles, but it would be better that you also read it, the text of the book. So please read it through in the book. So that is it for today's lecture. If you have got any question, I can answer now. Otherwise, we can